Welcome everyone. So my name is Cosmin Cojocar. I'm a security engineer at Google, and I'm also the maintainer of gosec, static code analyzer for Go. And today I will show some real examples and some security checks which are useful for, let's say, any Go project. The examples are based on mostly that they are all open source tools, and the CI part is mostly based on GitHub examples, because I think today most of the Go projects are hosted on GitHub. So the overview, the agenda for today, we will cover three big areas. So first we will look at the code security part, then dependency securities, and we will wrap up with the supply chain security. And if there is time, we will take some questions at the end. So if we look at code security, there are actually two big areas. One is static code analysis, which you might be familiar from other languages. In Go, it's no different. So there are tools, some of them open source, some of them commercials. They are using compiler techniques to identify security issues in code. And ideally, they should be integrated in the IDEs and also in the CI system. So we try to shift left as much as we can the security issues to be fixed by developer, ideally before the code gets merged. And typically they ship with a predefined set of rules, and yeah, they can be extended with custom rules. And normally all of them, or like most of them, they support a standard output format. It's called Sarif, which was standardized. And this makes easy integration across IDEs, CIs, and so on. Another area where we look at is fuzzing, so code fuzzing. It's probably a bit more unfamiliar, but we will have a look and try to see how it can be done in Go. So basically, fuzzing is just auto-generating random inputs in some interesting functions, and everything is kind of driven by code coverage. So the increase in code coverage basically will indicate that the input random data, it's something interesting to evaluate. So fuzzing, it's usually interesting in Go to identify edge cases which cannot be covered by unit testing. So now if we look at some code issues in Go, so we can see there are maybe some vulnerabilities or some issues which are familiar to you from other languages. So as obvious, we have input validation everywhere, and most of the time we neglect to sanitize it. Then we have all kinds of injections. Also because Go is used as a server-side, or like for cloud services or REST services, we can have server-side request forgery vulnerabilities. As well, we see a lot of unsafe crypto configuration in the code, because Go has a very good crypto library, like standard library. People, they use it, but sometimes it's not the safest way. Then, of course, there is stuff like path traversal, hard-coded secrets, cross-site scripting sometimes, because Go has these templating packages, and then can be used for HTML, and so cross-site scripting can be an issue. And nevertheless, also TLS configuration is an issue, because we see a lot of HTTP services based on Go, and TLS stack is integrated in Go. So people, they basically use TLS configuration directly from Go, but sometimes it's not the best. So the list is quite comprehensive. And now if we just look a bit on the input validation, we know, like as good software engineers, that input needs to be validated. But the question is, from where is coming this input? So just to list a few sources, so we know that we have a lot of command line arguments we accept in our binaries, files, environment variables. And nevertheless, in a HTTP server, we have the typical sources. So this list is quite comprehensive, right? So this can lead to a lot of injections, all kinds of injections, right? We have command line injections, we can have SQL, non-SQL, and code injection, whatever. So we see that the list of issues is really, really big. So now, if we think about manual code review, it's a good start, obviously. So we all do code review, but mostly not from a security standpoint. So security is very focused kind of code review sometimes. So basically, it's good to involve software engineers, but we don't have them most of the time. So sometimes there are big development teams with no software engineers. So it's kind of difficult. So it's not enough to do manual code review, but it's a good start, as I said. So it doesn't scale, obviously, because the development speed is high, right? And we cannot keep up with that. But we can use it, for instance, to detect design flaws instead of like trying to find the coding issues. It might be a more productive way to use it. And yeah, nevertheless, if we take into consideration there is also human error, right? So looking at all of this, there is obviously a need for automation. So now for code review, as I said, we have static code analysis. It's a good practice, and we must include this static code analysis in our build to detect as many as possible of these security issues. And we should try to fix these issues before we merge the code, to not let them to pile up and then have like a large amount of issues. Of course, the false positive rates is important, because if we have a high number of false positives, then we cannot trust anymore the scanner. So, and we waste time trying to triage. But on the other side, of course, we can have also false negatives, so the scanning is not complete. Basically, we will always have missed, let's say, security issues in our code. So it's not a, let's say, bulletproof option, but it's a very good, let's say, first line of defense. And sometimes if we want to integrate this scanning on the IDE, the speed is quite important. So developers, they want to have fast feedback. They cannot wait for like slow code scanners. And as I said before, it's important to have a standard to integrate. So Sarif it's a standardized way to integrate, and also to provide basically GitHub action or container images that these tools, they can be easy integrated. So now we in the Go community, we have a tool, it's called gosec. It's a community effort. I think by now it's like a 7 years old project. When started, was not many options, and it's a static code analyzer for Go. Basically is inspecting the abstract syntax tree and the SSA, the statics in a single assignment code representations. It ships with a set of rules which are implemented in Go, so it's relatively fast to run it. So it runs very fast, even in large code bases. It has a GitHub action which can be easily integrated. We will see in a minute an example how to use it, basically. And yeah, it's also integrated. Maybe you use, if you are a Go developer, Golang CI lint, which is an aggregator of many lints. So it's integrated in these tools or in GitLab as well. So yeah, you can use it through like a middle layer, which is not directly visible to you. And also has now a standard output format, which is called Sarif, and it can be easily integrated in let's say, tool like GitHub Advanced Security. We will see afterwards. So now let's have a look to an example. So we have here a simple server-side request forgery vulnerability. We have this code. We see here we have a simple URL, which it gets retrieved from query parameters, and then we do a request. So now if I run gosec on this code, I get some output, so it will detect the issue. We see that it tells me what is the potential problem. It provides some level of confidence severity. And also you see there is a mapping to the common weakness enumeration, basically, which is a standard. So this is like a basic output. But some developers, when they look at this output, they don't really know what to do. So it's a bit hard. And therefore, we try to enhance this output, and we integrated LLMs. So now we take an LLM and basically enable this LLM to provide an autofix for this issue. With a simple prompt, we send this to an LLM, and then this is what we get back. So we get more context. It's not ideal, but we see that it's more consumable for a developer, so it does not need to come back to a security engineer or, let's say, go somewhere to understand what the issue is. And also we can ask the LLM to provide a solution. So with some more details, this is basically what comes out of it. It's not perfect, but still it's a good start for a developer. So it's interesting that we can leverage it basically to improve the productivity of developers here. So as I said, it can be easily integrated. So this is an example of GitHub workflow. We have just one step here to add this gosec. It's a typical GitHub workflow. We just add it here as an action, and we generate the Sarif output, basically. And every time you open a pull request, you'll have the tool running and scanning. And what's interesting, because this Sarif is actually integrated with the GitLab code, let's say Advanced Security Center, and you will get directly the warning in GitHub Security Center, so you will see it exactly where it is, and you can action and fix it if you need to. So basically, as I said, we have by now 50 rules which they developed over time. They are implemented in Go. There is the full list of rules. They have a mapping to the common weakness enumeration. It's relatively easy to develop new rules in Go, but you need to understand a bit the SSA and AST code representation. And basically, the AST representation comes first from the compiler, and of course, it executes faster. And it's like you have to see it as a syntax, is like a tree, and it's suitable for like very, let's say, contained security issues where you know exactly the lines of code and exactly the pattern you want to match on. Is relatively fast, actually. But we have situations when we need to do data flow analysis, like taint analysis and so on. So SSA in that case works much better. Unfortunately, in Go right now, it's just possible to do it on a package level. We are kind of working, let's say, in gosec to build some sort of graph outside of the package to be able to link packages and have a more comprehensive SSA representation. Normally, when we run these rules against, let's say, big code base, they are all executed concurrently, so it's relatively fast. Okay, that's about code scanning. So let's move on to fuzzing. So this is like a fast intro to fuzzing. So basically, what fuzzing is at its heart is just we have an interesting, let's say, function we want to fuzz, and we generate random input into that function, and then we observe the function to see what's coming out of it. And here is a reference. It's a good documentation about fuzzing in Go. And normally, this random data is auto-generated, so we try to use code coverage to auto-generate data and discover new paths inside of the code. And I would say in Go, because it's relatively a safe, memory-safe language, it's more recommended to use it for complex code logic like parsers and so on, in order to identify edge cases which cannot be unit tested. yeah, you can discover. It's probably not the same, let's say not on the same level of effectiveness like in C++, where we try to discover buffer overflows and stuff like that. And yeah, in Go, there is this fuzzing framework, which has basically two modes. So one is a fuzz mode, when we basically fuzz the code and build up this data base of interesting, let's say, cases. And then there is a test mode where we can run the fuzzing as a unit test based on the existing data. So this generated corpus of data is stored under this test data path, and usually we can store it into the Git repository and then just run again the fuzz in the test mode, and basically it will run it as a unit test. It's good to basically keep the coverage up over time if someone is changing the parser and stuff like that. So here are some resources. There is a tutorial how to use it, and also Google has this OSS fuzz. It's a platform where you can submit fuzzers for your code, and it will basically generate, run the fuzzing for you automatically, and it will generate all the, let's say, findings, and it will do some sort of analysis and stuff like that. Okay, cool. Let's move to dependency security now. First, what are some good practices in Go? There are many dependencies for a variety of sources. So we pull data from GitHub mostly, but sometimes also from mirrors and stuff like that. So we should basically review this constantly, and yeah, it's not always visible, but we should check from where we pull dependencies. And also there is a tool which can be used to check the checksum of these dependencies. And of course, a good practice is to use bots like Renovate, Dependent Bot, and so on, whatever your favorite bot is, to keep these dependencies up to date. Yeah, another part is that we should always keep the Go version up to date, because there are a lot of security fixes and releases are quite frequent, and Go has a relatively comprehensive stand-up library. It's yeah, indicated to keep it up to date. But also we can scan continuously for known vulnerabilities. There is a tool, it's called govulncheck, which was created by the Go community. So this tool basically is able to scan the code, use basically static code analysis techniques to identify which are the active dependencies used inside of the code. It doesn't just look at the dependency configuration file. It really looks at the symbol table of the binary, and then it does a check inside of the code to see that really these dependencies are actively used. And there is also a vulnerability database. It connects to this vulnerability database, and it checks that really, yeah, these are vulnerable. So what we can do, we can basically integrate this tool inside of our build system and basically block the build every time there is a new vulnerability. It has some limitations. Basically, in Go, there is this reflect package, which is kind of, let's say, in a way, bypassing the type system. And sometimes if you use it, is not able to detect it, and also is not able to build a very comprehensive graph of the dependencies. So basically, this is how you use it. It's a simple binary. You can pick it up. And if you want to scan something, you just start it as a binary. We see here an example. I ran it against gosec a few days ago, and this was before Go 123.1 was released. We see here there are 3 vulnerabilities was detected, and also we see the whole path here. If we look at of this analysis, we see the full chain of calls, which indicates where these vulnerabilities are actually. So we can make an assessment and decide if we want to upgrade or not these vulnerabilities based on what we have. So Okay, now let's have a look at the first part, supply chain security. So this is it's a large area. I will just touch on signing artifacts, and especially signing Go artifacts. And sometimes we like Go is very used also for cloud native infrastructure, and most of the time next to binaries we release container images. So we want to sign both, right, binaries and container images. Also, we want to generate a bill of materials for an application. That's also a good practice to really understand which is the set of dependencies used by that application. We all know there are a number of tools, so sigstore and cosign. It's a like I think now it's an established tool to use. It's relatively easy to use. Yeah, we have here an example, so we can use it in different modes. There is this self-managed key, so if we have access to a KMS, we can store the keys in the KMS and then fetch them and run the signing process, basically. Or I think was shown before, we can use an OpenID Connect token identity to generate the token. And also we can use a classic way where we generate like a signing a key pair of private and public keys, and then we can use them in the CI system basically to sign. Yeah, here we have an example. So we have in Go, we have this tool Go Releaser, which is quite used by many Go projects. Here we have an example in this Go Releaser. Next to the release manifests, we have this sign manifest where we can add our cosign, and basically it will automatically sign the binaries with cosign, and it will everything. It will publish the signature and so on. So this is also relatively easy to integrate in GitHub. We have an example here. Let's suppose here we have this Go project. So we just need basically 3 simple steps. So one, I have an SBOM generator step. We can use another tool. This is just for examples. And then we have this release binary part where we call this Go Releaser tool with the manifest which I showed previously. And in case we want to release a container, we also need to add a signed Docker image, basically a container image step after we build that container. And basically that's it. And then, for instance, for the binary, we will see very often on GitHub, you see that there is this binary release, but next to it, we see the signature, basically. So now we can pick up this signature from here and check it with cosign if we need before using this binary. So I think this is what I had for today. So if we have any question, happy to take them.
Can you shed some light on gosec analysis sensitivity? Is it both path sensitive and context sensitive?
Yeah, I mean, there is basically, as I said, is using this SSA or AST representation. That's basic code context dependent. There is some basic data, let's say analysis, like you mean taint analysis, stuff like that. But it's not super comprehensive. So if you have like very complex code, it's not able to track to the entire call graph. So it's a small tool. If you need something basically to track the entire taint, I would recommend something like CodeQL from GitHub, or I don't know, SameGrep as well. It's to some extent it does that. Yeah, so it depends, but for CI, probably it's overkilling to use CodeQL. It's relatively slow and is more for security research if you want to really look at the code deeply and try to understand the code paths and stuff like that. But for CI, it's a bit slow, and it's yeah, not very quick feedback to developers usually. Okay, thank you.